All right, good morning. So at this point, all but three of you guys took the exam yesterday. I'm not sure what happened to the other three of you, but you should definitely have a conversation with me about that. Usually, what happens is my general policy is that I'll try to get exams back to people like the next time I see them. The summer school schedule, plus the fact that the exam was due at midnight last night, means that wasn't going to happen today. So I haven't actually graded them. I have looked over some of the responses, but not in a methodical kind of way. So I'll try to get those turned around and graded, hopefully by Friday, if not, certainly by Monday. Because I do try to have the turnaround time for exams be very short because it's a nerve-wracking process to have to deal with. So first things first, I guess let's talk a little bit about, test environments because we're using the Respondus browser to try to cut down on the level of cheating because there was a lot of that in my spring semester, and a couple of you guys didn't really take that very seriously. One of the things that it warns you, and I had to double check to make sure that it warned you, was that when you do that environment check, when you kind of pan your camera around before you take the exam, you're doing that to demonstrate to me that you don't have resources around that you're not supposed to have. Things like your cell phone that you can look stuff up on, or a secondary device that you can look things up on. So make sure that when you're doing that environment check that you're panning around so that that's clear, and that you don't have any of that stuff around. One of you guys, during the environment check, there was another laptop like next to you, and I don't think that you were doing anything untoward. So I'm not accusing you of anything, but it's probably better next time that you keep those other devices far out of field. I had a person in my other class who literally was on the phone during the exam. Uh, you can't have your phone during the exam. So don't make phone calls. Don't take phone calls. Set that two hours aside and do the test. Also, bear in mind that camera placement and lighting is important. It tells you that during the setup process. One of you in this class, literally the entire exam, I had a picture of the top of your head. I couldn't even verify that it was you taking the exam because all I could see was the top of your head until about like halfway. I had to scan through quickly, and there was at least one part where you moved, and I could see, it's that guy. I know that person, but you didn't do any of that stuff, and I can't tell what you're doing. You didn't do an environment check, so I can't tell if you're on your iPad or something on the side cheating on my exam. So please bear in mind that stuff exists so that you guys can demonstrate that you're on the level, because I don't want to have to doubt you guys. I hate using this stuff. I didn't use it last semester because I was hoping that I could trust my students because we're adults, and I think that we should all have a certain basic commitment to the ideals of honesty and the honor code. So it sucks that we're having to do this really big brothery kind of spy cam garbage to keep things on top of you. But at the same time, put forth the effort to demonstrate that you're on the level. And I'm trying to have your back here, guys. Don't make me be a bad guy. I don't want to do it. One of you guys took the entire exam like in a dark room where you could literally see nothing. Don't do that. Make sure the room is well lit. It tells you in the thing. Try to make sure that you don't have like backlighting so that you're silhouetted, because it's hard to see what's going on there. So please, for exam 2, take that a little bit more seriously, because I get little flags of this looks suspicious. Check this out, and I've got to watch all those stupid flags. And for some of you guys, literally your entire exam was flagged. So it's like, oh God, I have to go through all this just to make sure you're not doing anything untoward, and usually you're not. Also, and just for my own personal well-being, make sure you're dressed. Seriously, you're on camera, man. Ugh. I don't need to see that. All right. So as for the exam itself, I've gotten at least one you know, freaked out email that the first exam was tough and they had a bad time of it. And that's not uncommon. So if you had a rough first exam, that's typical, right? People often have a rough first exam in physics classes. It's a tough class. It's you've never dealt with it before. You don't know what to expect. Um, so hopefully it wasn't too traumatic. Bear in mind that I try to design my class in such a way that uh, the uh, the course uh, gives you lots of chances to pull yourself out from a rough start. So I drop your lowest exam. So if this was your lowest exam, it's going to go away. It's like it never even happened. I also have the final exam rule that says if you do better on the final than you did on the previous exams, it'll replace your exam average. So there's lots of ways to make a crummy first exam go away. So if you had a rough time, don't panic. Know that you got to make some changes to get where you want to go, but it's not the end of the world. So don't freak out. So having said that, let's go ahead and address the specifics of that exam. I do not want to do this. So, boom, that's what we want. So here was the exam, yada, 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 yada. Most of you guys were pretty good about uploading your stuff in a timely fashion. At least one of you like called me at like 11:30 last night because they were uploading their work on their phone and it was taking longer because they were doing it over the cell thing, and they wanted to make sure that I knew that was the cause of the delay. And that's exactly what I want you to do, right? If you have some sort of technical difficulty that is preventing you from getting that stuff there, that's what that Google Voice number is for. So kudos to the person that took the initiative to make sure to communicate with me about what difficulties they were having. That's what I want you to do. So this first exam, let's do these first questions. We had a total of really, it was 5 questions, but I broke one of them up into 2 parts. And so for this first part, you're driving at some kind of speed and you notice an obstruction ahead, and you've got to slow down before you hit the obstruction. But you have a reaction time, and this 0.45 seconds is not an unreasonable reaction time. That's about typical for a human being, and it means that you have to plan accordingly. So I put this on there because it's a one-dimensional kinematics problem, but it's a kinematics problem where you have 2 accelerations. Because before you hit the brakes, you're not accelerating at all. You're traveling at a constant speed of whatever they gave you. So you start off with an acceleration of 0. And then once you hit the brakes, your acceleration is going to be negative something. And that means you'll have to break this problem up into 2 sections. So that's what I was looking for, is could I get you guys breaking this up into 2 different sections? So let's work this through. Oops, I just passed it. Dagnabbit. So let's think this out. So in this problem, you've got a car and you're traveling at some kind of speed. And in the version I was just looking at, it was 22.9, but your number may be different. And you see some obstruction. There's some kind of thing up here in the road ahead that you're going to try not to crash into. And it tells you this distance. And for me, it was, what was it again? 54.6 meters. So somewhere up ahead. And what's going to happen is I need to make sure that I don't crash into that object. So hopefully what's going to happen is by the time my car reaches the position where that object is, my car will slow down to a stop. So I'm starting here. I need to make sure that by the time I get here, I'm stopped. However, complicating factors is that at first I'm not slowing down. So I'm getting closer to the obstruction. So between this moment and this moment, 0.45 seconds has elapsed. And when I get to this moment right here, I'm still traveling that same original speed. And during that whole section, my acceleration is 0. Now, during this whole section, I'm slowing down. So here, my acceleration is going to be negative something, right? I've got to be slowing down, so I have to have a negative acceleration during that section. So in order to solve this problem, I need to break this into two separate inventories, because remember, my 4 equations of motion only work if my acceleration stays constant, and clearly it wasn't constant. But it was constant from this moment to this moment. And it was constant from this moment to this moment. So I can do these as two separate little problems and put it all together. So let's do my inventory for the first section, right? Somewhere on my picture, I have to call x equals 0. And I kind of like that to be x equals 0. Let's have the positive direction be to the right. So what's going to happen is I'll have a starting position, an ending position, a starting velocity, an ending velocity, an acceleration, and a time. And during this section here, the time was given in the problem, and the acceleration was 0 during that section. Now, your starting velocity was given in the problem, and the ending velocity for that first section is the same because we weren't slowing down. My initial position had to be 0 because I'm calling that. My final position is however much closer I am, which I don't know. So effectively, what we've got to figure out is during that 0.45 seconds before you react and can hit the brakes, how much closer to the obstruction did you get? Because that's going to be that much less distance that you have to stop. So if I work it out that way, I'm looking for x final. Let's just use the position equation. Except for this problem, since the acceleration is 0 for this section, this whole term just dies a horrible death. And this, we started out at 0 as well. So we have x final equals v naught times t. You'll notice, by the way, that's the equation you guys learned in grade school, right? Distance is velocity times time. Yeah. So if I just take my starting velocity, 22.9 times the 0.45 seconds, that's going to tell me how much closer to the obstruction I get during that first 0.45 seconds. So what's that going to look like? Where's my stupid calculator? So 0.45 times 22.9. In my case, I'm going a whopping 10.3 meters closer to the obstruction. So now what's going to happen is I know where this is. I know this is at x equals 10.3 meters. So when I do the inventory for the second part, oops, I could just have that be my starting position. My ending position, I have to stop just as I get to the obstruction. If I stopped before I got to the obstruction, then I could have gotten away with less acceleration, and I'm trying to find the minimum acceleration possible. And if I stopped after the obstruction, well, I just wrecked my car. So I got to stop just as I reach it, and that'll give me my minimum value. So fortunately, that final position was given. My starting velocity right here, my velocity was still 22.9. And my ending velocity was 0. My acceleration is what I'm solving for. And I'm not really sure how much time it's going to take me to stop the car. I don't know. But I don't care. I'm solving for A. So what I'm looking for here is an equation of motion that has acceleration in it, but doesn't have time in it. So that's what I call the stopping distance equation. I call it that because it reminds me of problems like this all the time. And what's going to happen is I know that v final is 0, and I'm solving for A, so I'm going to take that over. Negative v initial squared equals 2a x final minus x initial. I'm solving for A, so it'll be negative v initial squared over 2 times how far I have to go. So now when I plug in my values, So V initial was 22.9. So 22.9 squared is 524, but there's a minus sign, so it's negative 524. Then I've got to divide by the denominator. Well, this is 54.6. This is 10.3. So if I take 54.6 minus 10.3, this parentheses is 44.3 times 2 is 88.6. And if I take the numerator, which was 22.9 squared, the 524 divided by 88.6, well, in this particular setup, I'm going to get a pretty nasty 2.9 squared divided by 8.6. I get negative 5.9. All right. So your numbers may vary. Generally speaking, the shorter this distance is, the higher that value is going to be, because that's going to be smaller. The faster you're going, the bigger that number is, the bigger that's going to get. Either way, no matter what, I expect the answer to be negative, because if I'm traveling in the positive direction and I'm stopping, I have to have a negative acceleration to stop at all. So if your answer was positive, that's definitely messed up, because that's somebody who sees something up ahead of them in the road and their response is to floor it, right? So you probably dropped a minus sign if that's what you ran into. So this first one was pretty straightforward. We've certainly done problems like that before. Let's go back to the screen share for a second. So what's happening in our second question? So this one was kind of a little bit tough. Probably, if not the toughest, certainly the second toughest problem on the exam. So I've got a person standing on top of a tall bridge. So here's a big old tall bridge. And there's my person. Oops, I'm drawing. So they're standing on top of a tall bridge. They drop a rock. They wait 1.54 seconds. So they wait a certain amount of time. They drop a second rock. And what's going to happen is when the first rock hits the water, the second rock is still in the air, and you know how far above the water the second rock is. And we're using that to figure out the height of the bridge. So just looking at that, it's not obvious, but if I switch back to my diagram, we can puzzle this out if we're clever. So here's my person, and what's going to happen is they take the first rock, and the first rock's going to go da 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 da. And so after 1.54 seconds elapse, the moment this rock gets to here, they're going to drop the second rock from rest. Now what's going to happen is this rock will continue down, splash. And when this rock hits here, this second rock has fallen, and we know that distance, or at least we did, 59.1 is the numbers that I've got. I'm going to call this distance D. So here's what's going to happen. What makes this problem tricky is that just like the previous problem, my accelerations change for at least one of the rocks. Because the minute I drop this rock, it's falling under the influence of gravity. It's going to have an acceleration of 9.8 the whole way down to the water. However, for the first 1.54 seconds, this guy has an acceleration of 9.8. The other rock's not moving at all. It's got an acceleration of 0. So this rock has an acceleration of 0 for 1.54 seconds. And then after that 1.54 seconds, then it will have an acceleration of 9.8 the whole time. So just like the previous problem, we're going to have to take this problem and split it into two little mini problems. One of those mini problems is going to happen while the first rock is not moving. And the second little mini problem is going to happen after it starts to move. And what makes this more complicated than the previous problem is that not only do we have two accelerations, we've got two different objects. So I'm going to have to do inventories for each object. So if it was me, here's what I would do, right? I would be like, look, this guy here is falling for 1.54 seconds while he's not doing anything. So the first little mini problem that I would do would be to figure out, after that 1.54 seconds, where is this rock and how fast is it traveling? Basically, figure out where this is. Then once you have done that, the rest of the problem, both rocks have the same acceleration. So I can do that one little mini problem of what does he do before I drop him, then do the problem of what happens as they're both falling. So let's do this little mini problem first. Forget the second rock. Don't even care about him yet. This guy here starts up here, ends down here. Now, I have to choose some kind of coordinate system, but the problem is I don't really know how far it is from the bridge to the water. So here's what I'm going to do. I'm going to choose an unusual coordinate system just to make my life easier. You don't have to do it this way, but it helps. I'm going to call x equals 0 the place where I drop the rock. And what I'm going to do is, since everything is falling downward in this problem and nothing's going up, I don't want to have a bunch of minus signs. Minus signs are annoying. So screw that. I'm going to call down the positive x direction. That way, everything's going to be positive. Now, for this rock here, I'll do his starting inventory. He's going to have a starting position, an ending position, a starting velocity, an ending velocity, an acceleration, and a time. Now, conveniently, by having this be position 0, that rock's going to start at position 0. It's going to end however far this is. We don't know that yet. We'll have to solve for it. Now, the initial velocity of the rock was 0 because we dropped it from rest. However, the final velocity of the rock, we don't know. It's going to be picking up speed the entire time it's falling. So by the time it gets here, it's going to be traveling downward at some speed we don't know. The acceleration, though, is going to be the acceleration of gravity, which is 9.8 meters per second squared. And normally I would probably put a minus sign on that because usually I like up to be positive and down to be negative. In this case, however, since I'm calling down the positive direction, I'm going to leave it as positive 9.8. Now the time is the 1.54 or however many seconds that this guy waits before dropping the second rock. So what's going to happen is I'd like to know how far down this rock is and how fast it's traveling. Well, I can use any equation of motion to do that. If I want to find the final position, I need to get something that has x final but not v. That's the position equation. So x final is going to equal x initial plus v initial t plus 1/2 a t squared. And x initial was 0. The v initial was also 0. That's going to take that whole term out. So all I'm going to have to do is 1/2 times 9.8 times my time squared. And that's going to tell me how far that rock will have fallen during that first 1.54 seconds. So I get this guy falling about 11.6 meters in my case. Again, your numbers may vary. So, yay, I now know how far this guy has fallen. This is right here, x equals 11.6 meters. So what about the velocity? How fast is it traveling? Well, I'll use the velocity equation. So v final equals v initial plus a times t. V initial was 0, so that drops conveniently away. So I'm just going to take 9.8 times the 1.54 seconds. And now I know how fast it was going. So 9.8 times 1.54 is going 15.092. I'm going to keep extra sig figs until the very, very end, meters per second. So now I know that when it's here, it has a velocity of 15.092 meters per second. That's not the answer to the question, but it's going to get me there. So what has to happen now? Well, now I need to do another inventory now that both balls are starting to fall. And this guy is going to start at this location. It's going to start with this position and that velocity. This guy starts at this position with a 0 velocity. So if this is rock 1, this is rock 2, well, let's call this rock 2 and that rock 1. So for rock 1, I'm going to have the following inventory, right? So what's going to happen is his initial position is going to be 11.6. His final position is going to be wherever the heck the water is. Now, the problem that I'm having is I don't really know what that position is. I know 0 is up here, and I don't know what that is. So X final, I'm going to leave that as a blank because I don't know how far down the water is. V initial, though, that's the 15.092 that we just found. V final is however fast this rock is going when it splashes into the water. I don't know how fast that is. I figure it's probably going to be going faster than this because it's still going to be speeding up the whole way down. But I don't know exactly what speed. I do, however, know that it's going to have an acceleration of 9.8 because gravity. And I don't know how long it's going to take to go from here to here. So that's unknown as well. So boy, does that look intimidating. I've got an inventory with 3 missing things, right? That's usually a harbinger of a difficult problem because most of my equations of motion I can't effectively use if I'm missing 3 things. So I'm a little scared just looking at that inventory. But that's for rock 1. What about for rock 2? Well, for rock 2, it's going to start, remember, rock 2 is way up here, right? It's at a position of 0. So it starts at a position 0. It's going to end, well, its final position is however far it is from here to here. I don't know how far that is. I know from here to here is 59.1, but I don't for any idea know what that is. So its final position, I'm not really sure about. Its starting velocity, I know that, that's 0. Its final velocity, I don't know that. Its acceleration is 9.8. And the time to go from here to here, I don't know what it is. However, I do know that however much time this rock takes to go from here to here is the same as the time this rock takes to go from here to here. So the one thing I do know for sure is that these 2 t's have to be the same number. So boy, is this messy. So I'm looking at this, and I'm trying to figure out how on earth I can figure out the answer to this question. And what will the answer to this question be? Well, I want to know the height of the bridge. Well, the height of the bridge is going to be the distance from where the rock started to the splashdown, which is going to be the X final for rock number 1. Aha! If I can solve for that, that will be the answer to the question. So that's the thing that I'm going to need. But the problem is, I don't have enough information here to do that. So, like, if this was your exam problem, you got to here and kind of crapped out on me, this is about 14 out of 20 points. This is, at this point, we're basically pretty doggone close to where it's going to turn into a math problem. And the trick here is realizing 2 things. One, the thing that unites this inventory and this inventory is t. So when I pick equations of motion, I for sure am going to pick equations of motions that have t's in them. Otherwise, I can't use these bits of information together. So definitely pick something with t's. The second thing is that since I'm looking for x final, I'm going to have to pick stuff with x finals also. So I'll definitely pick things with x's and t's. However, since I don't know the final velocity of either of these guys, I'm going to avoid anything with final velocities. So that's pointing me in the direction of the position equation. So what I'm going to do is I'm going to write the position equation for both rocks. However, what's annoying is that the final position of rock 1 is not the same as the final position of rock 2. They're 2 different numbers. So what I'm going to do is I'm going to call this x1 and this x2. They'll be different numbers, and I'll have to solve them. And somehow I'm going to have to make use of this 59.1 that they gave me in the problem but so far I haven't found anything to do with it yet, right? Anytime you get information in a problem where you don't know, like you haven't figured out what to do with it yet, that's a clue, right? That's a clue that that's going to be somehow useful. So we're going to have to figure out where that 59.1 comes in here in a second. But first, I'll take the position equation and I'm going to write the position equation for just rock 1. So x1 is the final position of rock 1, and that's going to equal 11.6 plus 15.092 t plus 1/2 times 9.8, that's 4.9 t squared. So here's an equation, and I can't solve it because I don't know x1 and I don't know t. Meanwhile, what about x2? So the final position of rock 2 is going to equal the starting position, 0, plus 0 times t, so that's going to go away, plus 1/2 at squared. Oh, that's just going to be 1/2 times 9.8 times t squared, or if I can simplify that, 4.9 t squared. So now what's going to happen is I have a formula that can tell me where this rock is. I have a formula that's going to tell me where this rock is. And I got to think about what can I do with that information. Well, on my picture, x1 would represent the distance from here to where the final rock ends up. So this whole distance is x1. Meanwhile, x2 would represent the distance from this rock to that rock. And here's the thing that I notice. Notice how x2 plus this distance right here is the same as that distance right there. That's an equation, right? It's not an equation I memorize. I'm looking at the picture and doing basic math. This plus this equals this, or this minus this must equal that. So what I know is that if I take x1 minus x2, that has to equal the distance d, 51.2. Well, that's pretty cool, because if I take x1 and I subtract x2 from it, I'll be subtracting 4.9 t squared. That means this will cancel this. And therefore, I will end up with d equaling just 11.6 plus 15.092 t. And remember, d is given in the problem as 59.1. And you'll notice that once I've done that, the only variable that I have left anymore is t. So I can subtract it. So I'll take this and subtract that over there. Then I'm going to divide by all this. And that's not the answer to the question, but it is the time at which the answer will occur. So it looks like this thing is falling for about 3.14 seconds. Now, what do I do with that information? Well, I'll go back, and remember, what I'm looking for is the height of the bridge. I'm looking for final position 1, but final position 1 is given by this equation, which I can now evaluate. And again, your numbers will be different, but you get the idea. I take that value of t and I'm plugging that back in. And I get, in this particular case, my bridge is a whopping 107 meters high. So what was the trick? How did I do this? Well, I knew that I had two different accelerations, so I broke the problem down into the when this guy wasn't moving for the first part, and then when it was moving for the second part. I figured out where rock 1 was at the end of that first part, and then for the second part, I did two inventories. And I recognized two things, that the time had to be the same, and that the positions, if I took the difference in the final positions, that was going to have to equal the 59.1. That gave me an equation that I could then use to solve. And the rest all kind of fell into place. So there was a lot going on in that problem. That was a tough problem. All right, what's the third problem? So the third problem is the obligatory graph interpretation question. And this one is pretty straightforward. I've got a velocity versus time graph, right? They're telling me a velocity as a function of time. And so I want to sketch a position graph and an acceleration graph for parts A and part B. I'm just going to do this on a screen share rather than switch over to the camera, because I can do this on the screen. So what's going to happen is, if I'm doing a sketch of the position versus time, then what's going to happen is the value of my velocity has to be the slope of my position. So for the first 1 second, you'll notice the velocity for the first 1 second is 10 the whole way, which means that for the first 1 second, my position graph has to be something with a slope of 10. That's a straight line. So what's going to happen is it's going to be a straight line with a slope of 10. Now, what's going to happen is at 1 second, the velocity starts off at 10, but it's going to start counting down and getting smaller and smaller and smaller and smaller until it gets to the 4 second mark. And at the 4 second mark, the slope, or the value of the velocity, is going to stop changing. So I need my slope to start off being 10, which is pretty steep. And it's going to have to get less and less and less steep continuously. And it will end up at a slope of 2. So it won't be completely horizontal, but it will be curvy. It will end up with a slope of 2, not completely flat. And then for the last 1 second, it'll be straight again. So what I expect is a straight section, a curvy section, another straight section. That's what I'm expecting my position graph to look like. Now, what about my acceleration graph? Well, the acceleration is the slope of my velocity question, or my velocity graph, which means for that, I'm going to be looking at what my slope is at various places. So for the first 1 second, my graph is horizontal. That's a slope of 0. So for the first 1 second, my acceleration is flat out 0. Then what's going to happen is, between 1 second and 4 seconds, I have a line that's straight, which means I have one value for the slope during that time, and it's going down and to the right, so it's going to be a negative slope. So abruptly, it's going to jump from being 0 to, oh my God, negative something, until it gets to 4 seconds. And then after 4 seconds, it's 0 again. So if I do this, like, it'll abruptly just jump down and look kind of like a big rectangular pit. And what's more, what's the value right here? How low is it? How negative is it? Well, I can figure it out. And in fact, I'm going to have to, because in part C, we're determining the acceleration at t equals 2. But the acceleration is the slope at that location. So I'm going to have to find that slope to answer part C anyway. So how do I find that slope? Slope is rise over run. So from here to here, what's the rise? Well, it rises from 10 down to 2. So the rise, the delta V, is equal to -8. Remember, it's final minus initial, so it's 2 minus 10, not 10 minus 2. The run is it goes from 1 to 4. That's a run of 3. So the delta T is 3. So the answer, therefore, for my acceleration is -8/3, which is -2.66 meters per second squared, not cubed. So right here, this value is -2.66. So that was the way that plays out, right? You just break down and interpret that graph, and that was what I was expecting. I got some crazy answers for that one, it looks like. All right. Question 4 was the straight up vector question. And this is one of those questions where, you know, sometimes I get like all kinds of weird drawings. And in order to solve this problem, you just got to break it down very methodically. So what it's saying in this problem is that I've got 3 vectors, and vector A has a magnitude of blah, blah, blah units. In my case, it's 9, and it points up into the left at some kind of angle above the horizontal. So the first thing I need to do is interpret what the heck that means. So here's vector A. It's up and to the left. They told me the magnitude, so this vector is 9 units long, and it makes, in my case, it was 58 degrees, a 58-degree angle above the horizontal. So here's horizontal. So this angle right here is the angle they gave me. That's 58 degrees. So this is vector A. Now, what about vector B? Vector B has a magnitude of only 6 units. It points down and to the right at a 30-degree angle with the vertical. So what does that mean? So it's down and to the right, has a magnitude of 6, so it's 6 units long. And actually, but they tell me that it makes a 30-degree angle with the vertical. Here's the vertical. So this angle right here is 30 degrees. And again, that's 6 units long here. So one is up and to the left, the other is down and to the right. What about the last vector? It points straight up and has a magnitude of 8 units. So vector C is straight up and 8 units. And what I'm doing is I'm going to imagine adding them all together. And when you add them together, you put them all tail to tip. So I can imagine drawing vector C pointing like that, vector A pointing like that, and vector B pointing kind of like that. And my final answer would be something like this, right? But man, that's complicated. I can't keep track of that. The scales are all weird. That's conceptually what I'm doing. But to do this analytically, what I really need to do is, instead of drawing this stupid picture, what I will instead do is take these 3 vectors and break them all down into their vector components. By breaking them into their vector components, I'm going to make the addition process easy, because all I'm going to have to do is add their components together to get the components of my final answer. So let's take vector A and break it into vector notation. Now, vector A is going to be a little bit to the left and a little bit up. And oh, look, that's a right triangle with a hypotenuse of 9. So when I go to break that down, the x component is the adjacent side of the triangle. The y component is the opposite side of the triangle. So what's going to happen is the x part will be 9 times the cosine of 58. That's the I hat component. The y component is going to be 9 times the sine of 58. That's the j hat component. Except the x component is to the left, so I'm going to slap a minus sign on the x component. The y component points up, so I leave that positive. And again, those are both numbers that I could calculate. 9 times the cosine of 58 is about 4.769. Ah. So again, I could take vector A and call it negative 4.769 I hat. And then 9 times the sine of 58 is 6.784 j hat. So I have the components for vector A. Vector B, I'll do very similarly. Notice it's down a little bit. It's to the right a little bit. This is the x component. This is the y component. But notice that when I draw it like that, since this is the angle that I was given, the y component is actually the adjacent side, not the opposite side. So I'll get the y component from the cosine, not the sine. And the x component is the opposite side of the triangle. So from SOHCAHTOA, sine is opposite over hypotenuse. So whereas here, the x came from cosine and the y came from sine, down here it's going to be the other way around. So for B, it will be 6 times the sine of 30 for the I hat component. It's to the right, so it's positive. The y component is negative, so it's minus 6 times the cosine of 30. That's the j hat component. And again, what's the sine of 30? It's 1/2. So that's 3. Minus, what's the cosine of 30? Square root of 3 over 2, which times 6 is about 5.196. So there's my values for B. Then what about C? Well, C is easy. It points in the y direction. It doesn't point sideways at all. So C is just equal to 0 I hat plus 8 j hat, period, end of story. So now when I go to add all these three things together, what I've got to do is add all their x components together. So if I call the total vector D, it's going to be negative 4.769 plus 0 plus 3. That's easy. That's negative 1.769 I hat. Then for the y component, I'll take 6.784 plus 8 minus 5.196. I'm not going to try to do that one in my head. I get 9.588 j hat. So we've done all this math. We figured out the two components of my final answer. But what does the question want me to find? It says I want to determine the magnitude of the sum of these vectors, and in my work to specify their direction. So what I'm expecting in the answer blank is just the number part. But to get full credit, you got to tell me in your work what the direction is. So let's think about what this means. It's a vector that's to the left because it's negative. Actually, let's draw it over here. It's to the left 1.769 units, but it points up much, much more, 9.588 units. So my final answer is this guy right here, right? It clearly points up and to the left, but how big is that vector? How will I find that? Well, I know two sides of a right triangle, and from the Pythagorean theorem, I know that C is going to equal the square root of a squared plus b squared, and A and B are these two sides. And so I can crunch all those. And I get 9.74. Let's call it 9.75 for sig figs. So this is the magnitude of my vector. It's 9.75 units long. But what would I have to say for the direction? Well, clearly it's up and to the left, but just saying up and to the left is very ambiguous because lots of angles, this is up and to the left, but so is this, and so is this. So I need to specify how up and to the left it is, and the way we might do that is with an angle. And for that, I could take the tangent of whatever that angle is and have it be equal to the opposite over the adjacent. So 9.588 over 1.769. So therefore, theta is going to be the inverse tangent of whatever that ratio is. So 9.588 divided by 1.769 is 7.819. Inverse tangent of that is 82.7 degrees. So my answer there would be that it's up and to the left, 82.7 degrees above the horizontal. Up and to the left. So that's unambiguous. It's up and to the left, and that's how steep the angle has to be. So the words are every bit as important as the number part. If you just give me a number, I'm not giving you full credit. So that was a straight up vector problem. I don't ask a lot of those, but vectors are pretty important. So I figured it might be test worthy. So question 5 is the obligatory comic book nerd question. It's also the obligatory projectile motion question because we're treating Superman as a projectile, right? He's moving in two-dimensional kinematics. And I wanted to have 2 blanks, which is why I broke it into 2 sections, but it's really just one question with a part A and a part B. So what's going to happen is, in order for me to solve this problem, what I'm going to have to do is draw myself a picture. And so here is the Empire State Building that Superman is trying to leap over. And the actual height from Google is that height. And Superman is going to stand somewhere over here. He's got a little cape. And what he's going to do is he's going to jump diagonally at an angle of 75 degrees. And when he does that jump, he's going to have some starting velocity. And what's going to happen is he'll have to go up and over and just barely clear the top of the building. And so in part A, we're trying to figure out what speed he's got to have to make it up that high. So the way you approach this is it's a 2D problem. So somewhere on my picture, I've got to have 0, 0. And I'm just going to go ahead and have Superman start at 0, 0. And I'm going to have the x direction be positive to the right, the y direction be positive upward. And when I take the inventory for Superman's motion, I'm going to have to do it using vector notation. So rather than call them x, we're going to call them r's. I'll have a starting position, an ending position, a starting velocity, an ending velocity, an acceleration, and a time. Now, his starting position, I had him starting at 0, 0. That was easy. So it's 0 I hat plus 0 j hat. Now, if he's going to barely clear the building, that means that at some later point, Superman's going to be right here, just barely above that building, right? So what's going to happen is he'll have to go sideways some distance, but I don't really know how far in front of the building he's going to have to be. So it'll be something I don't know, I hat, but if he's going to make it over the top of the building, he's got to be at least 443.2 for his j hat component. So that I at least know is locked down. Now, what about his starting velocity? He's going to jump at some speed, which I reckon is probably going to be pretty big. However, I got to split that starting velocity into an x and y component. So if v initial is some arrow that I don't know the length of. It's going to have an X part and a Y part. And what I don't know is this angle here is 75 degrees. And if I want to find just the X part or just the Y part, I got to use SOHCAHTOA. And again, from math, this part right here would be whatever his starting speed is times the cosine of theta. And this right here is going to be whatever his starting speed is times the sine of theta. Now, I can't get a number to this because I don't know what V initial is, but I can at least put these expressions into my inventory. So whatever his starting speed, cosine theta I hat, plus whatever his starting speed, sine theta j hat. That's the best I can do. Now, what about his final velocity? Well, if he's going to just barely make it over the top, that means that basically this is as high as he's ever going to get. And the useful thing about that is that if that's the top of his trajectory, at that one moment in time, he's not going to be traveling up and down anymore. So the y component of his final velocity has to be 0. The x component of his final velocity, I don't really know. So we'll leave that as a blank. Now, what about Superman's acceleration? Well, if we're assuming that he's affected by gravity just like everything else, and that he's jumping but not flying, because in the original comics he didn't fly, well, that's 0 I hat minus 9.8 j hat, right? He's gravity, same for Superman as everything else. And the time, we don't so much know. So, at this point, what are we trying to solve for? We want to solve for V initial. And V initial appears in one of two places, either the y component of his starting velocity or the x component of his starting velocity. And if I can get enough information to solve this problem, then I can do it from one inventory or the other. I may have to do something from both inventories. We'll have to look. And the thing that I notice is that in the y direction, I've got values for both the positions. I've got a value for the final velocity. I've got a value for the acceleration. The thing that I don't know anything about is t. However, everything else I know except for this. So what I can do is I can use an equation that avoids t, use the y half of the inventory, and I can solve part A in one step. That's the what I call stopping distance equation. Right? I'll take this equation and use it in just the y part of my inventory. So V final, I'm going to make be 0. V initial is going to be V initial sine theta. So V initial squared sine squared of theta. I got to square all of it because it's squared. Then I'm going to have plus 2 times, well, A is going to be negative 9.8. And x final minus x initial is going to be the 443 minus 0. So 443.2. And at that point, we're good to go. The only thing I don't know is this, because theta was given to be 75. So I just got to get V initial by itself. Since V initial is being multiplied by stuff, it's having stuff added and subtracted, and V initial is being squared. When you do algebra, we're going to do it in reverse order of operations order. So I'll deal with the square part last. I'll deal with the multiplication next to last, and I'll deal with the addition and subtraction first. So this whole term here is being added. I'm just going to subtract it from both sides. Notice when I move it over, I'll pick up an extra minus sign. It's going to cancel out that minus sign. So I'm going to end up with 2 times 9.8, but positive now, times 443.2. And that has to equal V initial squared sine squared theta. That's a number. I can calculate that. 2 times 9.8 times 443.2 is a whopping 8686. So now what I'm going to do is divide both sides by the sine of 75 squared. which again is a number. So if I take the sine of 75, that's 0.096. When I square that, I get 0.933. So it's going to be 8686 divided by 0.933. That's 9,310. And of course, to get V final, or to get V naught, I'll take the square root of both sides. So the square root of that is 96 point about 5. So go figure, that's pretty doggone fast. To give you a sense of things, 55 miles an hour is about 24.5. So that's about 200 miles an hour. So you want to jump over the Empire State Building? Yeah, you got to jump pretty doggone fast. Who knew? So that's the answer to part A. But what's going to happen when I go to do part B? So for part B, it says in the question above, how far from the base of the building must Superman be in order to begin his leap? Well, wait a second. On my picture, here's the base of the building, here's Superman. So what we're looking for is that distance right there. In other words, that's going to be the final position is what we need to find. So once we realize that, once I'm looking for the final position, is there an equation of motion that's going to allow me to solve for his final position? Max, shut up. For his final position in the x direction. We know the starting position. We know this now. We know this now. So we have a number for this. We know this is 0, but we don't know t. So is it possible to, Max, enough. Is it possible to solve for x final while avoiding both v final and t? Not so much. So in order for me to solve this problem, I'm going to have to do something to figure out some other element of that inventory. The obvious thing to do would be to find t. So I'm going to find t. How can I find t? Let's go back to the y direction for a second. We know that it started at this velocity. We know that it ended at this velocity, and we know the acceleration. Let's just use the velocity equation. We know that v final equals v initial plus at. V final was 0. And in the y direction, v initial is going to be the, what was it before? I forgot, 96.59. So 96.59 times the sine of 75, which is a number we can get, minus 9.8 times t. So if I add this over to the other side, 9.8t equals 96.59 times the sine of 75. And therefore, t is going to equal that velocity. Divided by 9.8. So 96.59 times the sine of 75 is 93.29 divided by 9.8. So this entire leap is going to take Superman about 9.5 seconds. Now, going back to my inventory, if I know that this is 9.5 seconds, and I'm looking for an equation that has the final position but not the final velocity, that's the position equation. Well, what's the position equation? X final equals x initial plus v initial t plus 1/2 a t squared, except that in his x direction, his starting position was 0, so that goes away. His acceleration was 0, so this term goes away. So it's just going to be his velocity times the time, which we already know. So his velocity will be the 96.5 times the cosine of 75, because we got to use the x part of the starting velocity, times 9.52. So it looks like Superman is going to have to be back away from the building to the tune of about 237 meters. Probably 237 or 238 when I round up. So he's got to have a pretty good clearance. He can't be right in front of the building because he's going to be moving forward the entire time he's rising. And in order to have enough time, he's got to back away a distance of 238 meters. So at the end of the day, that's another projectile motion problem. They're all basically the same. Do a 2D inventory and see if you can work stuff through. And I think that was it. So anybody still here listening? Let's find out. So all told, was this exam surprising? Were you like, I can't believe this problem's on here. I don't know what to do.
Yes, that was me.
Yeah. Bear in mind, I can see the video of you guys, which I can check to see if you're cheating. And I recall like seeing yours where at some point you're like, we never did anything like this in class. I'm like, you did. You just didn't realize it.
Yeah, I definitely was freaking out.
Yeah, you definitely were freaking. So bear in mind, remember, I designed my class because I know physics is tough and tests are hard, right? They're hard. I designed my class with that in mind. So the one thing that I will tell you is that, remember, I dropped your lowest exam and your final exam score can replace your exam grade. So there's lots of ways to make that go away. Normally during a regular semester, I do a kind of a drop and double trick where I take your lowest question and I throw it out and replace it with the biggest one. I don't think I'm going to do that for the online class just because I'm doing the quizzes in Canvas and it's harder to do that and without making Canvas explode. But I'll probably curve. So there will be at least a curve of some kind. But I don't know what it's going to look like until I grade everybody. So hopefully it's not terrible. The thing I will always remind you guys is that when you're in the midst of freaking out, don't forget that partial credit is your friend. Tell me everything that you could possibly tell me about that problem. So like if I was doing that Superman problem, just drawing a picture and saying, look, I know Superman's got to be backed up from here. That's going to be points. Breaking that initial velocity into X and Y components, that's going to be points. For those first couple of problems where you had the multiple accelerations, calling out the fact that the acceleration changed, that right there is points. So just writing, hey, from here to here, he's got an acceleration of 0, but from here to here, he's got an acceleration of negative something. That's points. And heck, even if you can't solve it, saying, hey, I don't know what the answer is, but I know it's going to be negative, that sort of information is also you demonstrating that you're thinking about the physics. That's worth points. So when in doubt, tell me as much as you possibly can, right? True story, when I got my PhD at Clemson, right, you have what they call PhD qualifying exams, right? And they were the worst exams I've ever taken in my life. There were 3 of them. They were 3 hours each. And each of those exams maybe had like 10 questions. And over the course of that week, taking those 3 exams, I can guarantee you that there are maybe 2, maybe 3 questions that whole week that I know for sure that I got completely right from start to finish. The vast majority of them, I got partial credit, right? But I passed that test with flying colors, and a lot of it was because when I'd get stuck on a problem, maybe I had some big gnarly bunch of math and I couldn't figure out how to unknot it. What I would do is I would write, okay, look, I can't figure out how to simplify this expression, but if I could, this is what I would do with it. And I would detail what I would do if I could get past the place where I was stuck. Or, I don't know what the answer is, but I do know that, for microwave radiation, I expect wavelengths about this big. And for infrared radiation, I expect wavelengths about this big. So I'm telling them, I kind of know sort of how things fit together. And I'm demonstrating to the people who are grading that if I wasn't in a stupid exam, I'd know what to look for. I'd know where to go look to find the answer that I'm seeking. And that sort of thing demonstrates a proficiency that we're looking for. So if you can tell me that, if you can tell me, hey, if I could solve this equation for t, I would then do this with my value of t, that's going to be worth some points, even if you couldn't solve that first step. So, when you're in the midst of it and you're kind of freaking out, don't hesitate to write down what you're thinking and, over explain it. Tell me everything you know about that stupid problem, because every little thing is points. And hopefully in the process of you explaining all that stuff, maybe it'll jog your memory, or, you realize, oh, wait a second, I do know this thing. I just didn't realize it. Because remember, a lot of times in these problems, there's stuff that's kind of in between the lines. Like, oh, I don't know the acceleration. Oh, but wait, it's gravity. I do know. They didn't tell me that it was gravity, but I know how gravity works. Gravity gives me an acceleration of 9.8. So tell me what you know as much as possible. And I'm looking for excuses to throw points at you guys. Right? I've got some students who, have taken my class multiple times, and it's because they got into the final exam and they freaked out and they turned in a blank paper. Right? If you turn in a blank piece of paper to me, I can't give you points for that, right? So tell me as much as you can, and go for as much partial credit as you can get. I am the king of giving partial credit, if you give me an excuse to give you some partial credit. All right. So overall, my feeling is that you guys are probably not super comfortable. I know Jasmine has sent me an email after saying this is not a good test for me. But other than that, how do you feel like you guys did? Do you feel like maybe some of these you at least did pretty well on?
I feel like I got the basics of the questions, but I think once like I tried to unpack like the complicated part was where I started to like real freak out, because I was like, okay, like this don't look familiar to what we did like with homeworks and stuff. So that's why I was freaking out, because I review like based off homeworks and stuff. So
Well,
I was like,
homework, I'm trying to teach you some tricks, and then I'm trying to give you test questions where you're using the same kinds of tricks, but they're not going to be the exact same questions. So it can be bewildering, but hopefully that's what's going to happen when you guys get good at this. I'll be able to throw any kind of question at you, and you'll know how to react to it.
yeah, but my problem is too, like, I have a problem with like words. Like words trip me up real easily. So I think that's also where I was kind of like, okay, yeah, this doesn't make sense. But if it was just to be like numbers, I could figure it out, because I know what number goes to what in this and third. But I feel like certain words I'll overthink about, because I think the one with the last 5 and 6, I completely like blank, because I was just like, okay, I don't recognize the words that this is talking about. Like these words don't look familiar to a problem that we've done before. So I was kind of like, okay, I was like, I don't even know. I was like, I don't even know what to do at this point. So I was kind of just like trying to now, but it's crazy because when you just went over it, like I kind of had the idea of what to do, but I just couldn't put it on paper, because I like the steps to getting to it was what was getting to me. So yeah.
Yeah, I hear that a lot. I know. I remember when I was like in elementary school, and we would take math classes, and I had so many of my fellow students were like, I hate word problems, right? Those are the worst. And for me, I never had that issue. They were like, it's just another math problem, man. It's not a big deal. And I think that part of it is like when you run into that issue where you have like this word problem you're trying to unpack. One of the things that might help, or it always helped me, was I would kind of translate the original words into my own kind of wording. And a lot of times when I'm drawing my diagrams, what I'm really doing is I'm kind of working through what's going on in this problem. Because sometimes when I try to paraphrase or unpack like what's happening, when I'm drawing that diagram and sketching how the thing is moving around, I'll start to notice, oh, wait, this is projectile motion, and I know how to do those. So maybe that's what you can do, is get into the habit of kind of talking yourself through it. And hopefully by trying to sort of paraphrase or explain to yourself what's happening, you'll start to pick up on those little context clues that are hidden in that problem. It's definitely, it's tough. It's definitely hard, but it's doable. You just gotta keep with it. So, all right. So I'm not going to do anything new today. So this is pretty much what we're going to spend our time on. If there's no other questions, I'm going to let you guys go. Again, just to reiterate, when exam 2 happens, and it's probably going to happen about the middle of next week, Um, you know, I would make sure that your test environment is well suited for taking an exam. Make sure that in your neighborhood you don't have, or in your vicinity you don't have your cell phone. I don't even want to see it, because then I have to start wondering, when they look off to the side, are they looking at their paper, or are they looking at their cell phone? And if I have to, if I have doubts, that's when I throw the red flag. Um, so make sure that that area is clear, and then during that environment check, make sure you're demonstrating. Oh, look, there's nothing over here. We're cool. Uh, Make sure you do that. Also, if you have some issue that prevents you from taking the exam in a reasonable way, be upfront with me. I'm pretty lenient about how we do stuff. What I mean by this is I had a student who I think is in my other class, and she's in the process of moving right around the time that my exam is happening. And this poor girl, she had a hard time getting Lockdown Browser installed, so she didn't start the exam until Wednesday. But in order to get it done on time, she had to be doing the exam in the car on her mobile hotspot while her mom drove her to her new house. And she's like, the mobile hotspot kept not working and it was rough. And I'm like, no, if you're going to have to do it in the car, tell me, no, I don't want to do this in the car, because I'd rather you not have spotty Wi-Fi. I would have gladly just given her an extension until like the next day to take the exam. But once you open the exam, you're stuck, right? So if you feel like there's something that's going to mess you up, tell me about it. We'll see if we can't work something through. I have some people in my other class who still have to take their exam because of stuff like that. I'm not heartless. I'm not unwilling to be reasonable for stuff, but you got to tell me in advance, because once you start, it's out of my hands, right? Because you only get one attempt, and once you've seen the exam, then I can't prove that you didn't take those questions and go look stuff up. So it's got to be something you do in one sitting. So make sure you're well set up for it before you do it. Jasmine, you had a question?
Yes. So we don't have a lab due tomorrow, right?
No. Last week we did like lab report boot camp.
Yeah, because I remember like checking in, and you were like,
Yeah.
"You don't have to be here," and I was like, "I just want to make sure like we didn't have anything due."
Yeah. Watch the video. It's up there. I've just moved a ton of videos off of the Zoom cloud and onto the Canvas thing, so that's there. And again, I'm walking you through. Hey, these are things that I'm seeing in your lab reports that you need to do better. So watch that. See if any of those things apply to you. And if you've got some of those early lab reports where maybe you're doing some things that are substandard, if you change them in the very, very, very near future, I'll grade the revised version as opposed to the original version, because I'm trying to give you guys some
Okay.
heads up. But yeah, there's not a lab due on Friday, but we will have a new lab that will be due the next Friday. We'll be doing something next week or this week.
Okay, that's all I needed.
All right. All right, folks. Have a good day. I'll see you guys later.
Thank you.
You're welcome, folks.